Okay, so good morning, and thank you to the KTN and to eFutures for giving me this opportunity to talk to you this morning. And I'm going to tell you a bit about our research and some of the early results that we've got from our work on the International Centre for Spatial Computational Learning project that kicked off a number of months ago. Now, my own research interests are around the energy efficiency and the management of energy efficiency in electronic systems. And that's kind of a systems level approach that goes from larger mobile and embedded systems, which is kind of what I'm going to be talking about today, all the way down to the highly constrained microcontrollers, potentially self-powered devices that make up the kind of leaf devices and sensors in IoT. Now, I don't think it's a surprise to anyone watching this that we're seeing an increasing desire to move inference in AI systems out to the edge. And that could be for privacy reasons, kind of giving a boundary around where your data goes and retaining it on your local device rather than sharing it with the cloud. But it's also for a number of technical reasons. So that might be latency requirements you have. In a self-driving car, you may not be able to accommodate the latency of sending data to the cloud, having it processed and fed back before you make decisions in your control loop. It might be because of the available bandwidth. So there's a statistic there that the traffic lights in Las Vegas generate 60 terabytes of data a day. You probably don't want to be sending all of that off to the cloud, and therefore probably in that case a more distributed edge device processing approach makes more sense. There may also be connectivity issues in that there are some applications where you can't guarantee network connectivity at all times, and therefore if you want to be able to provide a reliable service, you might need to push that intelligence down to the edge. Now, one slight caveat just to note is that it doesn't necessarily get rid of those problems by doing so, it just moves the problem. And so if you've got high latency or low latency requirements and large amounts of data that you're transforming around, potentially that gets just as difficult, if not more difficult, to accommodate at the edge. But it's a different problem. Also, we're becoming increasingly aware of the power consumption that today's AI models are consuming. Now, admittedly, most of that, or a large chunk of that, is for the training rather than inference. But there's a statistic here that's up until 2012, the power that we needed to do our compute was increasing along with Moore's law. So every 2 years it was doubling. But since 2012, we've seen that increase by almost an order of magnitude. Now, pushing AI out to the edge doesn't necessarily solve all of this, because it is probably, at least to start with, the inference we're pushing, and the training is the large amount of the consumption. And it doesn't necessarily solve the problem anyway, but it's a motivation for why we need to solve it, because it's not going to be possible to have those same power budgets on edge devices. And so it's kind of an indirect benefit of moving things out to the edge. So we want to do inference at the edge. We get these benefits, but ultimately the platforms that we have at the edge are constrained, and they're constrained in terms of the resources that they have available on them, from compute to memory to power consumption and energy. And if we consider the kind of metrics that we might consider for our AI workloads, we're all going to be very familiar with our accuracy, so just over 70% here. And that accuracy is typically platform independent. It doesn't matter what platform you run it on, it's going to do the same computation, it's going to run through the same model and get the same result. The thing that might change is the amount of time that it takes to get that result. So, for example, on the Odroid XU3, we can get the fastest result in just over 100 milliseconds using the largest, fastest processing core. However, that is also the highest power consuming of all of those operating points on the Odroid, and also nearly one of the highest energy consumers. Therefore, we might have wanted to take a different option and run at 700 megahertz on the A7, giving us the best energy consumption. Or we might have wanted to kind of make a compromise on that 1.3 gigahertz line to give us a moderate execution time with a pretty low energy consumption. But the message here isn't really that there is one right or one wrong answer that I'm trying to advocate for. It's that we have an operating space that is a trade-off between execution time, power, and energy. In this case, not accuracy, but I'll come on to that a little bit later. Now, we're starting to see more and more specialist accelerators for AI on embedded devices, as well as other platforms that are popping up, and there's just a selection of them there. And these are helping to both make our AI workloads faster and more energy efficient. But they don't necessarily solve the problem. They're a different compute engine to add into our already complex system. And solving these kind of design challenges are easier in some systems that are, as I'm referring to here, reasonably static. So maybe it's a real-time system, maybe it's a system that is an embedded system that has one task that it's going to do repeatedly and in a controlled way. But I would argue there's a number of areas and application domains where this isn't the case. And it might be that it's a general purpose system like a smartphone, where it might be running an AI model, or it might be running two AI models at the same time, and that might be alongside some graphics or some augmented reality, or a game, or a number of workloads going on in the background at the same time. It might be a multi-tenant system where it has one model, but lots of different people are able to, or lots of different users are accessing that at different times. Or, as I think we often see in IoT systems, which are typically kind of inherently event-driven, it might be that they are having to adapt to the environment around them. It might be that external stimuli are what are driving them to perform the computation. So, for example, it might be an object tracking network, and the system therefore depends on how many objects are detected in the scene as to the amount of computation that is needed to track those objects. And so these are more dynamic systems where it's more difficult to design the solution to meet the requirements onto a particular platform. And that's this idea of being able to manage the resources that we have. And I would argue that the complexity has grown considerably over the last couple of decades. Before then, we may have had one or maybe two CPU cores in our system that were the available resource, the available processing resource that we could use to execute tasks. And we now see systems that have multiple CPU cores and multiple heterogeneous CPU cores. We might have GPUs that we can use to offload and accelerate computation. We might have an FPGA fabric that we can use. We might have neural accelerators. And then instead of just having a small number of devices that we might want to design for, we might have a whole host of different smartphone platforms and architectures that we want to be able to run our application or our model on. And if we're talking about coexisting with other workloads and other software on these platforms, we're in a situation where there might be tens or hundreds of thousands of different workloads that could be coexisting. And if you consider all the combinations of all of these, we're talking millions or billions of combinations at any point in time. So it's a very complex space to try and manage that interaction. And there's a few examples there of current or reasonably recent SoC platforms, just to give you an idea of the heterogeneity and scale of processing elements that are available. And so I'd argue that managing resources is increasingly less trivial, but is increasingly needed to manage the kind of workloads and the kind of operating space that we have. So coming back to our AI models, the question I would pose is, if you were trying to solve this problem at design time, how would you develop a model, or you have developed and trained up a single model that can fulfill your application as best as possible, but now you're looking to deploy it onto different systems. And so how do you design that model so that it can run on a wide range of different platforms with different resources and different resources, both in terms of the type, but also the computational ability of them. So some are going to be less able than others, for example. And then beyond that, how are you going to do it so that they can all provide the same level of service, whether that is in terms of frame rate or latencies and so on, or whether it is in terms of the accuracy of the model that they're outputting. And actually, maybe in different applications or different use cases or different user requirements, there are actually a range of different requirements that we want to be able to operate. So some of the existing work in this area effectively uses offline model pruning, where you prune away filters from the network that are less impactful on the end result, in order to compress your model, make it smaller, and also make it faster to compute. But the issue with that is if you were trying to solve lots of these different problems, and then if you were also to consider some of the dynamism that exists when you're running it on that platform, you end up needing a massive library of different versions of the model, all of different sizes and so on, that you can switch in and out. And so that kind of takes us on to some of these runtime challenges of really how we can execute our model while meeting timing requirements that there might be, so frame rates or latencies, how we can do that within power budget or within energy budgets and power envelopes, and also how we can meet the user and the application requirements. And so to give you a kind of an example of this, if you consider the dummy architecture on the right hand side there, if we want to execute a DNN on it, then maybe we use a small CPU core to do some of the pre-processing, and the neural accelerator to run the model. That would be a sensible thing to do. However, a small time later, maybe we want to run another DNN on that same system, and maybe it's got higher computational demands, and so therefore we move that first neural network off onto the GPU, and we move the new neural network we put onto the neural processing unit. And maybe in order to do that that migration onto the GPU, maybe we had to scale the model slightly, because it would not be able to do as much on the GPU for the same energy envelope or timing allocation as it would have been able to do on the neural unit. Then maybe a small time later, another task comes on, and this is a graphics intensive task that requires the use of that GPU. So at this point, maybe we have to move one of those MPUs off onto some CPU cores, and again adapt our model to fit on that resource. And now we're looking at a system that's being quite heavily loaded in terms of all of those different resources that are available, and they're also all interacting with each other, and they will have had implications on the interconnect and the available bandwidth in terms of how they're interacting with each other. But at this point, when it's very loaded, the temperature is probably increasing, and before too long it will probably violate the thermal bounds on the skin temperature, for example, and we'll need to throttle back its performance. So in this case, maybe we reduce the VR application down, perhaps by scaling the quality or the frame rate. And we're also going to transition or migrate back our DNNs onto the MPU, but they're going to have to scale down in size so that they can both run alongside each other. So this is just a dummy example to give you an indication of some of the challenges that I see and some of the things that we have to cope with. But in order to do all of this, we need to have our DNNs that we can scale and change. And by scale here, I'm meaning in terms of their execution time, but also potentially their quality of service or their quality of experience in terms of the accuracy that they're delivering, or maybe the number of classes that they work across, and so on. But basically, in terms of the service that they're providing. So we need some DNNs that are dynamic, and there is a research area around this. We're not the only people working in this area. But what I'm going to talk about is one approach that we've looked at called incremental training with group convolution pruning. And so what we're doing here is we take a model that you can see at the top there, and we break it down into, in this case, 4 different groups. Once we've done that, in order to train the network, we start by ignoring 3/4 of the network, so 3 out of 4 of the groups, and just training group 1. Once we've done that, we then freeze the first group and start training up group 2. So that group 2 is now benefiting from if you like, the knowledge that has been learnt in group 1 and adding to it through the training process on group 2. And then we repeat that process for groups 3 and groups 4 as well. And what this gives us is an incremental network where we can just use the first group, so just use 25% of the model, or we can make that model larger and allow it to perform better. And you'll see that in the results that I'll present to you in a minute. In order to experiment with this, we modified AlexNet so that it worked with the CIFAR10 database rather than ImageNet. And you can see that we've taken the AlexNet model there on the right-hand side, and we split it out into these 4 different groups. We experimented with it on 2 different platforms, the Odroid XU3, which has 8 CPU cores at 2 different sizes. It does have a GPU, but we haven't used it in these experiments. And then we also looked at the NVIDIA Jetson Nano, which has 4 CPU cores and an NVIDIA GPU. And so if we look at the results, to start with, if you focus on the right-hand side, so this is showing the impact or the trade-off between the size of that model and the accuracy that it delivers. So if we use the 100% model, that black dot at the top right, that gives us the best accuracy. But if we scale back and use our smaller model, the 25% model, that drops the accuracy down to 56%. So the question might be, why would you want to do that? Well, making the model smaller means there's less computation, which makes it faster. And so we would hope that that would then have an impact on things like the energy consumption. And so if you look at the left-hand side graph, that is then looking at the trade-off between energy consumption and classification time that results from operating those 4 different size models, which are the 4 different colors, on 2 different types of processing elements. So either a smaller A7 CPU core or the larger A15. Now, if you were to make some observations for this, the first I would probably say is, if you were trying to find kind of as you stare at it, the area that you want to operate in, you probably think is right there down in the bottom left, because this is giving you that Pareto curve of the best trade-off between energy consumption and classification time. However, it's only part of the picture, because all of those dots are green, therefore it's the 25% model offering the lowest accuracy. So as well as being able to trade off energy and time, we want to be able to trade off accuracy as well. So that means we want to consider all 4 of these different Pareto curves between those 2 parameters. Now, the one note I would say on that, though, is while we probably don't want to operate at those right-hand points, the ones that haven't got a line over them here, and that is because, for example, with the 100% model, the black dots or the black crosses, if I had an energy budget of 200 millijoules, I would prefer to be able to do my computation in just under 200 milliseconds, rather than the other dot, which takes 400 milliseconds to do the same computation in longer time. However, it might be that other applications executing on other cores in the cluster are operating at a lower frequency, and therefore I can't access those higher frequency points. Or it might be that I have a thermal budget or a power budget here that I'm trying to meet at a point in time, and therefore I can't operate at those higher frequencies. And if we look at the relationship between power consumption and classification time, as we slow down the frequency on our CPU, we save power. So if we're trying to meet a power budget, it always makes sense to go further to the right. If we look at the Jetson, you can see we kind of have a similar result. The right-hand side is identical because the same computation is being performed. The left-hand side here is a bit more sparse, and that's just because we haven't accessed as many operating points on that platform. What we do have is, as well as having the CPU points, we also have the GPU points, and as you would expect, they're a lot faster in terms of classification time, and also more efficient in terms of energy consumption. So what these plots have shown you really is that we now have an ability to explore this operating space and this trade-off between time and energy consumption, but also accuracy as well, and pick points that we might want to operate at to meet whatever our metrics are at any point in time. But it doesn't solve our original problem of actually how do we design systems that are intelligent and manage this and trade off different requirements of different stakeholders with the available resources that they have. Now, I'm afraid I don't have the answer to this. I don't have a slide which gives you a successful result that does this and manages everything effectively. And this is ongoing work for us at the moment. But what we're doing here is we're lending from some of our previous work. So we were involved in a project called the Prime project that finished a couple of years ago, and this was looking at how you manage resources in these kind of multi-core heterogeneous systems, but not for AI workloads. And effectively, the approach that we looked at and the approach that we're starting to lend from and apply to our AI systems are based on this 3-layer approach on the right-hand side, where we've got our runtime software in blue in the middle, and we have a runtime manager, the RTM, that's operating alongside our scheduler. And that runtime manager is the intelligence in the system trying to glue all of these things together and make clever decisions. And it reacts to what's currently happening, predicts what's happening in the future, and controls things appropriately to try and get the best outcome. It relies on having a set of controls, so that might be hardware controls like changing frequencies, mapping tasks, scheduling tasks, turning on and off processing elements, or it might be software controls. So in the case of our DNN, that might be changing the size of the model between that 100% down to 25%. Or it might be enabling or disabling different classes that our model works across. In terms of monitors, we then also want to look at what's happening on our hardware. So that might be looking at temperature or power consumption. It might be identifying bottlenecks in the system. But it also means monitoring our software, so looking at whether or not we are meeting our timing requirements, and potentially looking at whether or not we are getting the desired accuracy or confidence on our classification results. And it then glues all of those things together to try and make best decisions across lots of applications operating on lots of different processing elements. And so our ongoing work at the moment that we're getting towards the point of having some very interesting results from is really taking on board all of these things that I've talked about today in order to try and manage the execution of our AI workloads on these systems. So to conclude, as I said at the start, AI is moving towards the edge, as I think probably most of the people watching this agree with. But there's going to be a big difference in that the available resources on edge platforms are not just smaller and more constrained, but I believe that they're more dynamic in terms of their availability as well. And I think we're going to see a move towards systems that don't necessarily provide the best operation, and that best could be interpreted in all kinds of ways, from throughput and timing to accuracy to other factors. And I think we're going to see this kind of shift of what results people get and what people are willing to put up with. And there's an interesting quote at the bottom here from Professor John Norton, an emeritus professor from the Open University, whose area is in the public understanding of technology. And he made this point that companies are going to learn to make these trade-offs, though it's going to have unintended and antisocial consequences too. And I think this is important because you're going to be talking about edge services where where you're not necessarily providing the best output that you can, or the most accurate output that you can. And so if you have a self-driving car that's got a number of different algorithms, AI algorithms working at the same time, some of those are going to be more important than others. Some are going to have different requirements in terms of accuracy, in terms of time, safety critical and non-safety critical, and how they all balance together within a constrained resource budget in order to make the right decisions in the right time, I think is quite an interesting one. But I think it's one that we're going to have to tackle if we're going to get energy efficient edge AI. So I just wanted to quickly acknowledge Li Jun, the PhD student who's leading on lots of the work that I've talked about today. Then also the International Centre for Spatial Computational Learning, which this research is being done under the umbrella of. And also the Prime project, which is the thing I presented a couple of slides ago on the previous research we've done in this runtime management area. Other than that, thank you very much for listening, and I'm more than happy to take any questions that you might have. Thank you very much.